Hi guys, let's do number of islands. So we're given an m by n 2D binary grid called grid, which represents a map of ones, which are land, and zeros, which are water, and they want us to return the number of islands. So an island is surrounded by water, and it's formed by connecting adjacent lands horizontally or vertically. We may assume all four edges of the grid are surrounded by water. So in example 1, we would return 1, because basically if the land is connected horizontally or vertically, then these are connected horizontally, and these are horizontal, and like these are vertical, and like so on, right? So like this whole piece of ones are all connected somehow, either horizontally or vertically, and there's no other like disconnected ones here. So there's only one total island, so we'd return 1. In example 2, we return 3 because these are all connected either horizontally or vertically. This one's connected to nothing, right? Horizontally or vertically, it's all zeros, so this is only connected to itself, which counts as its own island. And these two are connected to each other, but nothing else. So these two are an island, and so we would return 3 because there's 3 total islands. So in this one, unlike the last one that we did for number of provinces, where we were given a grid that represented edges, right? Because like if we had a 1 in that one, it was representing that there is an edge from I to j. In this one, the 1 in a certain coordinate means that this is a node itself instead of an edge. So instead of having to create a hash map to map the nodes to all of their neighbors, we can actually just access the neighbors directly here, because it's just the ones that are directly above, below, to the right, or to the left of this node. And we can do that by manipulating the coordinates in the grid, right? So like if this is at 1, 1, then to explore this node, we would just explore 2, 1 or something, right? Because like, so like, and so like if while we're like looping through the 2D array, then we just change our values, like so I plus 1 or I minus 1 or j plus 1 or j minus 1 to get to the neighbors. So we can actually just do that directly here. We don't need to create any like data structures for that. Although we do need to keep track of the nodes we have visited somehow, because we're going to do a DFS basically for every single node and its neighbors until we either reach water or are out of bounds, because then we've reached the end of this connected component, right? So we need to keep track of what we've visited so that we don't end up revisiting the same nodes over and over again. Because like if we have visited all of these, let's say, and then we get down to like we backtrack over here somehow, and then we get to this node, then we don't want to go back to this node because we've already seen it, right? So you can do this several ways. You can either keep track of I think the easiest way for this one is creating a Boolean array of the same dimensions as our grid here, where true means that we have already visited that coordinate and false means that we have not seen that or visited that coordinate yet. That's one way. Or another way, which is what I'm going to do, is once you've visited a node, you can actually just edit this directly and like sync the land, if you will. So this 1 will become 0, because we're not going to explore any zeros because that's water and we only want to explore the land. So once it becomes a 0, then if we get back to it, we're not going to revisit it because it's now water. So that's another way. So to start, we're going to want to keep track of how many islands we've seen so far. So we'll initialize that at 0. And then we're going to need to loop through our grid here. So for I is 0, I is less than grid.length, I plus plus, and then same thing for j. 0, j is less than grid.length, or grid at I.length, sorry, because they're not exactly the same, or not necessarily the same dimensions, right? This is 4 by 3 or whatever. So then we're going to want to check, so like we're starting at 0, 0, right? So the node at 0, 0 is a 1. So we're going to want to check if the value is 1. And if it is, then we know that it's land. And if we have found a new piece of land, which will be the case here, we will want to increment our islands, our number of islands that we've found. So if grid at I at j equals 1, then islands will be incremented. And we'll do a DFS to explore all of its neighboring nodes that are also land. So we will explore neighbors. So we will pass in our coordinates I, j, and the grid because we're modifying the grid directly. So like basically for, this is like starting the DFS, but then we're gonna have another DFS method that will call itself with all of its neighbors. So we'll only increment the islands if we found a new piece of land that's not connected, because if it is connected, we'll call it within the method itself, if you get what I'm saying. And we will need I and j, because to visit the neighbors, we'll need to modify I and j, like I plus 1, I minus 1, j plus 1, j minus 1, and the grid, because we are modifying the elements directly in the grid. So, and because we need to access the grid in the DFS to get these coordinates in the first place. So that's like another thing. And then at the very end, once we've explored the entire grid, then we'll have found all of the islands that there are in here, and we'll just return the number of islands. Okay, and then we need to do our DFS. So private void DFS, we'll pass in I, we'll pass in j, and we'll pass in our grid here. And for our base case, so our base case is like when we want to exit the DFS, and so we will want to exit when we're either out of bounds in the grid or we have found a 0, because if it's water, then we don't need to explore it. So if I is less than 0, or I is greater than or equal to grid.length, or j is less than 0, or j is greater than or equal to grid at I.length, or grid at at j equals 0, then we will just return, we'll do nothing. Okay, and if not, then that means our current node must be a 1 and it must be in bounds, right, if we haven't returned yet. And if that's the case, we will want to change it to 0 so that we don't revisit it again. So grid at I at j will become 0. And then we'll do a DFS on all of its neighbors. So DFS I plus 1, j grid, DFS I minus 1, j grid, and I j plus 1, I j minus 1. And I think that should be it. Perfect. Okay. And then our time complexity here is going to be O of n times m, where, I mean, you could define this however you want, but I guess technically m times n, we could say that because that's what they give us here, but you can really just say whatever, like, because you define your own variables. We could say m is number of rows in grid, n is number of columns, like, you know what I mean? Like, you can say whatever. But basically the reason why this is the case, okay, is because if we think about our algorithm, we are exploring our entire grid, every single row and every single column. So that is already going to be an m times n, and you can see that in this for loop here, this nested loop, right? Because we have to explore every node in this graph no matter what. And we're doing the same thing in the DFS by exploring all the neighbors, right? Because this isn't really like doing anything extra, like we're just exploring all of its neighbors, and we're not really going back to its neighbors, because if we've already seen that node, we're not revisiting it, so it only gets, like, every node only gets counted once, even though like there's recursive calls here going on. So I know it's like kind of weird, but just like logically, if you think about it, like it kind of makes sense. And then our space here is also going to be the same thing, so I guess we could say m times n, because, so, okay, we don't have any additional data structures other than what was given here, which doesn't really count because it's the input. But since we're doing a DFS, then worst case, okay, like, let's say worst case, our entire grid was, okay, this is gonna take forever, but okay, sorry guys, I don't know why I decided to do this, but like, let's say worst case, our entire grid is all ones like this. Then in that case, our call stack, okay, or our call stack in our DFS, because every time you go deeper and deeper into the DFS, you know, because it's like a recursive call, it is putting more stuff onto the stack, and we don't actually remove them from the stack until we are backtracking in our DFS, and then we remove the nodes as we backtrack. But if it's all ones, then basically the worst, and this is the worst case possibility, then we are adding all of like the entire grid onto our call stack before we can backtrack and remove them all. So worst case, this will be m times n, which is the same thing, like number of rows by number of columns. So I hope that makes sense. Thank you guys for watching, and like and subscribe if you found this helpful. Bye!